Hello, everybody. Let's finish our conversation about the effects that the Earth's atmosphere has on the ability for us to do astronomy, to use telescopes. In the previous video, we talked about how the atmosphere can blur images, or how it actually does blur images. It's always blurring the images. And we quantified what we called astronomical seeing. How much does the atmosphere blur out our images? That was all for visible light, the kind of light that the human eye can see. In this video, we want to ask ourselves about the rest of the electromagnetic spectrum. We want to ask ourselves what wavelengths of light over the entire electromagnetic spectrum make their way all the way to the ground. So which parts of the electromagnetic spectrum can we observe from Earth? Because if 0% of the light makes it from outer space down to the surface, here we are sitting at the surface, we can't observe those wavelengths out in the universe because our atmosphere is acting like a wall. And I want to use that idea of the atmosphere as a wall to define what is called atmospheric opacity. It's a fancy sounding phrase, but it's really kind of simple. It's just a description of how much like a wall the atmosphere is for that part of the electromagnetic spectrum, for that wavelength of light. And it'll work where 100% opaque, a atmospheric opacity of 1.0, means no light makes it to the ground from outer space. So the light is coming from outer space, comes to our atmosphere, and by the time it gets to the surface, none of the light has made it. It's all absorbed by our atmosphere. Our atmosphere does not let that light reach the ground. In this case, the 100% opaque, an atmospheric opacity of 1, the atmosphere is the same as a wall. Like this notepad, for visible light, has an atmospheric or has an opacity of 1. The light is not going through the notepad. However, radio wave light has no problem going through that notepad. Okay, so an atmospheric opacity of 1 is 100% opaque. That means our atmosphere will be a wall. 0% of the light reaches the ground. An atmospheric opacity of 0% opaque, would mean perfectly transparent, 100% transparent. So all of the light at that wavelength would reach the ground. 100% of it, none of it would be lost, which means that we could observe it from the surface of the Earth. And of course, there's every bit between the 0 and the 1, the 0% and the 100%. So let's imagine there's a wavelength of light that is coming down, it hits our atmosphere, and by the time it gets down to us at the surface where our telescopes are, only 50% of the light made it down. 50% of it was lost. Our atmosphere absorbed it. That would be an atmospheric opacity of 0.5 or 50% opaque. A atmospheric opacity of 0.3, 30% opaque, would mean that 30 or 70% of the light made it down to the surface. 30% was blocked. An atmospheric opacity of 0.8, 80% opaque, means that 20% of the light would make it down to the surface. 80% was absorbed by the atmosphere, didn't make it to the surface. So this is going to tell us, if we look at how opaque the atmospheric opacity of our atmosphere over the entire electromagnetic spectrum, we can see what kind of astronomy we can do from the ground. So in this figure up here, in this graphic, we have very, very short wavelengths, 0.1 nanometers, a tenth of a nanometer, very, very short wavelength, and even shorter over this way. And it goes to the very longest wavelengths. So here's 1 kilometer, that'd be a radio wave that has a wavelength the size of a mountain to even larger. And then what we're seeing in the brown here is how opaque, how much like the wall the atmosphere is. 100%, an atmospheric opacity of 100% opaque. So none of this part of the electromagnetic spectrum makes it through our atmosphere, 100% absorbed, which is great because that is gamma rays, X rays, and ultraviolet light. The high energy light that is also called ionizing light is also the dangerous ones where you put a radiation symbol on it because it does things like sterilizes life. That's a nice way to say kills it. So we're very glad that our atmosphere blocks this high energy radiation. But that means that we can't observe gamma rays, X rays, or pretty much any ultraviolet from the ground. You might be thinking, Dr. Lindsay, I get sunburns. That's from UV light. And you can see that, yes, the longest wavelength ultraviolet light, the ultraviolet light just more violet than violet, a very small percentage of it makes it down to the Earth's surface. This is the safer part of the ultraviolet spectrum. And you might have heard of UVA, B, and C. Those are going to be that part of the ultraviolet spectrum. And even though a tiny fraction, say 10% or less of that light reaches the surface, that's still enough to give you a nasty sunburn and cause things that can happen in your life like skin cancer. So it's still extraordinarily dangerous. All right, so we don't get gamma rays, we don't get X rays, we don't get ultraviolet light. But here, the atmospheric opacity dives down. Nearly all of the visible part of the spectrum, electromagnetic spectrum, makes it to the ground. We can do visible light astronomy. We can look out into outer space and see the stars. If our atmosphere was opaque to visible light, we could not see the stars. That starlight would never make it to the surface of the Earth. So, visible light is a window where we can observe the universe. Here in the infrared part of the spectrum, it gets pretty crazy due to all the atmospheric molecules with their infrared molecular lines. So, it's really, really hard to observe the infrared from the ground. We get a nice narrow window right here where some people try to do astronomy, but it's pretty tricky. And then you have a nice wall of an atmosphere for a good part of the microwave spectrum, the far infrared and the microwave part of the spectrum. You get a couple of very narrow windows. You get a big window where 100% of the radio wave light makes it all the way down to the surface. And then longer radio wave light is blocked by our ionosphere, reflects off of a part of our atmosphere. So this shows us that what parts of the electromagnetic spectrum make it to the ground. And let me go ahead and block out all the parts that don't make it to the ground. So what's left on this graph is what we can observe from Earth. We have two primary windows. We have two big regions of the electromagnetic spectrum that we can observe from the Earth. We have the visible part of the electromagnetic spectrum, and we can observe all of it. And we have radio wave, and we can observe a huge swath of radio waves, make it from outer space to the surface. So we have a bunch of radio waves. This gives us what we call our primary spectral windows, windows to the universe, where we can observe that part of the electromagnetic spectrum. So our two primary spectral windows are visible light and radio wave light. This is why when we talk about the next part, we'll talk about radio wave astronomy, radio astronomy, because we can build radio telescopes on the ground. We have talked only pretty much about visible telescopes because that light reaches the ground. If you want to talk about everything that we can possibly observe, notice that this part of just redder than red, what we call the near infrared, it's near to the visible spectrum, just barely infrared. We can observe that pretty easily from the ground. So we can build ground-based telescopes to observe visible light, near infrared light, radio wave in this region of the spectrum, and just a tiny, tiny, tiny bit of microwave. You get a couple of tiny windows there, but it's pretty difficult. So this leaves us for the rest of the electromagnetic spectrum. If we actually want to see what the universe looks like in X-ray light, if we want to see what it looks like in infrared light, if we want to see what it looks like in microwave light, we have to send telescopes to outer space. And it was actually Lyman Spitzer, whose name is Lyman Spitzer is the person that gave the name to the Lyman series of hydrogen, although he didn't call it the Lyman series, it was named in his honor. And Lyman Spitzer also has a famous space telescope named after him, the Spitzer Space Telescope, which was an infrared telescope. But this person, all the way back in 1946, proposed to the United States government the first space telescope. And everybody was like, whoa, cool, awesome. This is a great idea, but we couldn't really do it yet. Well, we have other priorities. So we didn't launch the first space telescope until 1968. So now 50 years later, we've only had 50 years of doing space-based astronomy. We are really just getting started on this. Since then, we have created space telescopes that can observe the entire electromagnetic spectrum. Not every possible wavelength, but at least some wavelengths within every part of the electromagnetic spectrum. In this graphic right here, let's pay attention to the space telescopes. So we need space telescopes for everywhere where this plot is red. Every place where the atmosphere is a wall and doesn't let any of the light down to the surface. And we have some pretty amazing observatories. So the great observatories of NASA, which include things like Fermi, Galix, Chandra, Hubble, Spitzer. But what do we have? Well, we have the Fermi Space Telescope. The Fermi Gamma Ray Space Observatory is its official name, and it observes in the gamma ray. I wouldn't call it a telescope because it doesn't focus light, it just collects gamma rays. The Swift Telescope operates in the X-rays. Chandra, still active, operates in X-rays. Same with New Star, operates in X-rays. Galix is now retired, but it operates in the ultraviolet part of the spectrum. Or no, Galix is still operational. Galix is still operational, and it operates in the ultraviolet part of the spectrum. Hubble operates a little bit in the ultraviolet. It's sensitive in the ultraviolet. Spitzer, which is now fully retired, was an infrared space telescope. We don't currently have a operational infrared space telescope. Herschel was in the infrared as well, but it's no longer operational. The Planck telescope operated in the microwave part of the electromagnetic spectrum, and it observed the leftover light from the Big Bang itself, or really about 350,000 years after the Big Bang. Whenever light was free to go out into the universe, it decoupled itself from matter. The light echo from the Big Bang, called the cosmic microwave background. So Planck was designed to go observe that. And then there are a few others. We have not had a whole lot of space-based telescopes. We're always trying to build more, but they're very expensive and it's very difficult to design these missions. From conception to launch to collecting data is typically 20 to 30 years of effort. So we have a lot of them coming down the pipeline, but for most of the electromagnetic spectrum, we need space-based telescopes. And I would love to see increased funding so we can eventually cover the entire electromagnetic spectrum with the sensitivity that we want, because there are simple discoveries out there, things that we could just look and be like, holy cow, we didn't know this existed in the universe, just because we don't have a space telescope capable of observing it yet. So we are at the forefront of discovering what's out there in the universe. We have done a lot of work, but we're nowhere near where we need to be. All right, so effect of the atmosphere requires us to make that the atmosphere is a wall in most of the electromagnetic spectrum, requires us to make space telescopes, and we're just getting started with that. All right, thanks for tuning in.